And there are a couple things on there that I realize I didn't mention that are important. I'm going to mention them now. They're basically terms, and these won't, I'm not going to, out of all the terms I could pick, I won't pick the ones I'm just reminding myself that I should mention. I won't put those on the exam, but, there's always the final, okay? So let's some neglected subjects from, let's call it midterm 1. And this will not be on midterm 2. And so there's a couple terms. I don't think I mentioned these. So too bad, right? Because these are, I know you guys like these terms for some reason. Extensive and intensive. So what does that mean? I mean, I think you know kind of what intensive means in day-to-day life. That was like an intensive review session where we really went over a lot of stuff. But that's not what it means here. Extensive are thermodynamic quantities that scale with system size. I'm gonna erase that intensive. I was not planning ahead. So, for instance, U, V, F, H, A, like N, this is the number of moles, etc. And so here's a small coffee, and here's a large coffee. And so let's say this has an internal energy, U small, and here's U large. And U large equals is greater than U small, right? So if I have a large coffee, it has a bigger internal energy than a small one. The volume is bigger, the entropy is bigger, right? And so things that scale with system size. But what about the temperature? So if I have a small coffee and I say, oh, make it a large instead, it's coming out of the same urn. Does a large coffee have a higher temperature than a small coffee? Someone said at the office hours, probably not. You know who you are. But no, it doesn't, right? Because that's an intensive quantity, and intensive quantities. If I'm defining a term, I should probably write it so that you can read it. Let's see if I can actually do that. Quantity that is independent of system size. Now you have to be a little bit careful. Like what I mean by this is if I have a given thermodynamic state, okay, and let's say I have an ideal gas at a given thermodynamic state, and then I double its size. So all the extensive variables double, but like the temperature doesn't double, the pressure doesn't double, and things like that don't double. So intensive examples: T, P, and this mu is, which we're just now starting to talk about. chemical potential, and if you don't know what that is, this is the thing, enthalpy and chemical potential are the two things I disliked the most when I took undergraduate thermodynamics. But I've gotten over it, and I hope you don't develop the same phobias. But we'll talk more about what chemical potential is as we go forward. And typically, like T is the derivative So where did I get that? Because I know du is T ds minus P dV, right? And so the temperature is that derivative of U with respect to S. And U and S are extensive. And T is it's a derivative of one with respect to the other, but if you go back to the definition of derivative being like, df dx is delta f divided by delta x, and you take some limit where delta x gets small, it's really a ratio. So T is a ratio of U and S. And so the extensive part cancels out. And so like a derivative of an extensive variable with respect to another extensive variable is an intensive variable. And like P is minus partial U partial V at constant S. And so these are intensive. I can't believe, maybe I just don't remember mentioning this, but I can't believe I didn't mention that, right? That's one of the early terms that you need to mention, but it's on that sheet. And now that should answer the question of like WTF, does this mean, and will it be on the midterm? And so this is what it means. But like I said, there's plenty of other definitions that I can put. So I'm not going to put this one on the midterm. But for the final, that's another matter. Okay. Then there's another thing that I didn't talk about, and I'll mention it right now. I don't think I talked about this. Free expansion. Okay? So let's do our, let's say we have a gas. Let's make it look random. So we have an ideal gas. Again, not on midterm, but we'll be on final probably. Ideal monoatomic gas, 1 mole, the usual. And it's in a volume V naught. And here we have a partition. And over here, in there we have a vacuum. All right, so we have a gas that's in we have a big container with a volume of 2 V naught. We put a partition in, kind of like a magician would do, and like when they saw somebody in half. Don't do that at home. But there's a partition in, and all the gas is on one side. Now we could make that partition a piston, and we could expand the gas reversibly, right? So we'll do an irreversible free expansion. And by free, I mean, this is equivalent to P external equals 0. Okay, so I could let that piston. I could let that partition could be a piston, and then I could just untether it or like remove the little pins that keep it from sliding, and then it would be free to slide. but there's a vacuum on one side, and there's a gas with a pressure on the other side. And what pressure does the vacuum exert? Zero. So what'll happen to that? What'll happen to that partition? It'll just slide freely as the gas expands against an external pressure. The other thing I could do is I could remove that partition. Okay, and then what would happen? Like if I'm really quick, I pull the partition out so fast that the gas molecules don't have a chance to move. So they're all on one side of the container, aren't they? Well, what'll happen within probably picoseconds or nanoseconds? I don't know. They'll spread out. Okay, so we can calculate the usual things. Delta U, and we have a constant. We'll do it isothermal. So delta U is going to be equal to Q plus W. What is the work? Zero. There's no work done. Okay? And so what is Q? So the gas, U, is 3/2 RT, right? And no work is done. And so this could be adiabatic, or it could be isothermal, because it doesn't matter, because the gas isn't doing any work. It's an ideal gas, so these particles are bouncing around, and they're bouncing off the partition. Then I pull the partition out, and then there's no partition to bounce off of, but they just keep going until they hit the far wall, and then they bounce off that. So each molecule is undergoing elastic. Now we're channeling our physics, right? Undergoing elastic collisions with the boundary of the box. So the molecules are not losing any kinetic energy, right? And so Q is 0 because delta T is equal to 0. Now this is an ideal gas. So I have a gas, and its initial pressure. There's an initial pressure, right? There's an initial volume, and we do this expansion. V naught goes to 2V naught, right? T naught doesn't change. No work or heat. P naught goes to 1/2 P naught, right? Because PV equals RT. It's an ideal gas. So the pressure is half as much. The volume is twice as much. The temperature is the same. No work is done. No heat goes in or out. So it's this, and so these like, so well, we'll get to that one. Oops. Delta U is equal to 0. Delta S is R log 2V naught over V naught, which is my favorite answer of all, right? R log 2. And so because U and S and H and G, I didn't ask you to calculate those. You have an example of doing exactly that same process, though, reversibly, right? When you do it, or if you do it irreversibly, isothermally, you get to the same final state. If you do it reversibly, you do work, and heat goes in because it's isothermal. The temperature wants to go down, but you can't have a difference in temperature. We've said this many times. But you get from an initial to a final state. Here you're getting from the same initial to the same final state. Delta S is the same. Thank you. I have a present for some of you. Thanks. Yeah. See you. That was a very unenthusiastic round of applause. Anyway, so we those are the exams for those of you who haven't picked them up. We'll do that at the end. but of course, the entropy of the universe is different. So delta S of the system is R log 2. So this is a free expansion. This is a problem where I don't think we ever did a free expansion problem. We can do it. There's another variation of it, which I'll talk a little bit about someday that I don't feel like doing anything else. We can have call it a hatch. So we can do this problem. So we have a hatch that's closed, and we open it. Or we could have a leak form in something, right? We could have a spray can where we push the nozzle down and the hatch opens. So by the way, when you have a spray can and you spray it and you spray and spray and spray like you're not supposed to do, like these damn ants, I'm gonna just take care of them. And so you're spraying and spraying and spraying, and you feel the can. What do you feel sometimes? It gets cold. Why is that? Because it's not an ideal gas, right? So you have whatever, it has pretty high pressure in there. The molecules in there, and maybe there's some other things I'm not taking into account, but there's a potential energy of interaction. And then when I put them into a bigger volume, it takes energy to break those weak, attractive interactions. And it's sort of like an endothermic reaction, right? So energy is going to have to go in the form of heat to do that. So why does it happen? There's one word. What property, what thermodynamic quantity is causing this to happen? When I open that hatch, it expands, and it's not because there's no energetic benefit, if you will. What is the quantity? Entropy, right? And so the gas wants to get out. It's like a bunch of cats, right? A gas wants to get out of the can, goes out. Delta S goes up, but heat is going in to make that happen. So that's because it's not an ideal gas. So we can calculate. So delta S was R log 2, work was 0, Q was 0, delta U was 0. Delta S of the surroundings for the reversible one, heat went in to the gas and it came out of the surroundings, right? So the surroundings delta S was negative for the reversible one, but here it's 0 because no heat had to go in. And so this is the most irreversible possible expansion you could do, because delta S of the universe was delta S, which is always R log 2, right? For this process, doubling the volume, isothermal, it's always that R log 2. And there's 0. No, well, let me write it what it is. Right, and so that's delta S plus 0, which is just delta S is R log 2. Might as well answer it. So if this were on an exam, and again, this won't be on the midterm, but what about the final? Okay, so the answer is delta S of the universe is R log 2. For any of the other, for the reversible expansion, that surrounding one exactly canceled, and I got 0. Because if I say it's reversible, there's one thing that you should know, is that delta S of the universe is 0. And if I say irreversible, then delta S of the universe is greater than 0. Those two things exhaust the two possibilities. But normally for an irreversible one in the middle, like with the constant force, half P naught, then it was somewhere in between. I subtracted something off, but not enough to make it 0. Okay. So I'll give you a problem. Let's say, so let's say I have a gas in here. I'll give you this problem. So let's say I have out in deep space. Okay, I have a gas in a container, and the container develops a leak, and this could happen, right? And this volume here is V equals V naught. So what is delta S of the universe? It's greater than zero, but what is the value? I want a number. So, and let's say the gas, it wouldn't be a gas, but let's say the gas was at the same temperature. Well, I mean, the gas could be at some temperature, okay? And if it's an ideal gas, let's say there's nothing in the universe but this gas, okay? And the gas expands, and it's an ideal gas. What is the temperature of the gas after it expands? Well, strictly speaking, it's the same as it was initially. So we have a very dilute ideal gas in a universe that has the same temperature as it started. But so let's say let's say it's isothermal free expansion. Okay, what is delta S? And there's one mole. What do I put in here? Well, I put V final over V naught. What's the final example? What? Well, it's the volume of the universe. I put this on an exam once, and I said, calculate delta S of this process. I'll give you the problem. I won't put it on an exam. But what I said was, state your assumptions. Okay, and then on the front or on the back of the exam, there was some data, and one of the pieces of data was the distance to the farthest known object in the universe. So the way I would do that problem, and I said I needed the volume of the universe, and this is however many light years. I would say it was 4/3 pi r cubed, and r is the distance to the farthest visible object in the universe. But what you find when you do because of the logarithm, like you could assume that the universe is even twice as big, and delta S doesn't change all that much. So because of the logarithm, it's pretty sensitive to that. But anyway, so that's free expansion. And should I talk about this now, or should I talk about? Yeah, I'll mention this because this is also something that won't be on the midterm. Has anybody heard of Maxwell's demon? Yes. Okay. Who is Maxwell's demon? Well, that guy Maxwell. That you're going to have fun with Maxwell you will have fun with Maxwell on the exam, because there will be, in addition to some definitions, there will be some Maxwell's relations to do, because they look impressive, but they're actually easy. And I want to say, look how smart my students are. Look how good a teacher I am. Look at the mean on this exam. Right? I want to and they look like they're hard, don't they? But are they hard? Are Maxwell's relations hard? If you don't learn how to do them, they are, right? And they'll baffle you. But there were some examples. There were 4 of them on the homework, and there's more than 4 possible Maxwell's relations. So there'll be maybe some of the same ones, maybe some different ones. So that's the same Maxwell, and he had this idea. This is like the free expansion kind of in reverse. So we have our box, and we have our partition, and we have our hatch, right? So that's the hatch. We can open and close that. And we have some molecules, right? And because the volumes on either side I drew to be roughly equal, so I put the same number of molecules on both sides. And by the way, we know that S equals K log W, right? Because Iwan told us that. And how many, like if I put, I could do this. So I have the same, this is supposed to be the same picture. So which of those two pictures is more likely? What? Yeah, it's sort of it's slightly subtle. These are identical particles, let's say, but there's more ways to put it in the top one, right? So W is bigger here. Like I take the first one, I have more choices where I put it, and it's a combinatorial problem, okay? And there's only one way to do the lower one, all on one side. So but based on that formula, entropy is going to go up if I, if it's going to spontaneously do that, because the dynamics is like always. There's a lot. There's like chaos theory comes into this. You ever saw Jurassic Park? That cool guy. The water. Laura Dern has caught his fancy, and so he's telling her about drops of water. This is the butterfly effect. The butterfly flaps its wings, and because exponential sensitivity of the equations of motion, like a slight error in integrating numerically these differential equations or solutions will diverge. This is chaos theory in a nutshell. That's wrapped up in why this thing, if it was evolving, they would go on one side. You could have a system that wasn't chaotic, and you'd have all six of them would be bouncing back and forth from one side to the other forever. There needs to be a mechanism whereby they kind of randomize their motion, or randomize is like our perception of something that is really deterministic but has a sensitivity. Okay, but you would agree that if I start in the bottom picture, I come back later, it's going to look like the top picture. So what Maxwell's demon does, let's see, he's a demon, right? So he should be red. Right, so here's Maxwell's demon. So he's looking at that picture, and why can't you do this? So Maxwell's demon, opens and closes door to sort molecules to one side. So like if let's say he wants to do that. He wants to go from the top picture to the bottom picture. So if this molecule here is going to do that, right? He shuts the door, right? But if this molecule comes, he lets it through. Okay, so he lets molecules go from one side to the other, but not from the other side to one. So he sits there and just watches and does this. Could you do that? What stops you from doing this? Well, there's always a second law, but it doesn't stop you from doing this. In fact, I had some undergraduate research students once, and they wrote a Java video game that does this. So this was back in the Java days. But you could play it, and you'd have some particles, and then you have a certain amount of time, and you could open. It was like Pong. You know this game Pong? Like, think of anti-Pong. Instead of having a paddle that would move, you had an anti-paddle that would move. And then you'd put the anti-paddle to let the things sort. So you had a certain amount of time, you'd sort them. Then it'd be more, and then you'd sort them. And then, it wasn't that much fun. But to play, but it was okay, So you can actually do that. Now, does this violate the second law of thermodynamics? What do you think? Well, it doesn't, and the answer why, people thought about this from the day of Maxwell, which is like 1800s, and Einstein thought, all these different people thought about it, and they finally figured it out. Well, I think people still think about it in like the 1980s, which seems like a long time ago to you. But actually, I enjoyed the 1970s, so this was actually after, I was an adult. So it was in relatively recent times where sort of the thermodynamics of this was actually sorted out, and it has to do with information. So, like, if you're Maxwell's demon and you're looking at this, you're making a record. There's a disk drive somewhere that starts out having zeros in every register, and then you're putting a 1 or a 0 depending upon if you're going to open the door or not, let's say. And then at the end of the day, you have this rather complicated thing that contains information that is the result. And now, if you're going to make a cycle, okay, you could like, and you probably have this idea. I hope you do have this idea that, like, you could have, like, you take a gas that's compressed, and you do a reversible or even an irreversible, as long as it's not free, expansion, right? And the gas does some work, and the energy that turns into work comes from the surroundings. So you can take heat and turn it into work, but just that one step, okay? To make it a cycle, to be able to do that, like the Carnot cycle, there's more to it than that. You need to go back and recompress the gas, okay? And so this Maxwell could is the demon. Maxwell is delegating this to the demon. The demon could do this. Then you could attach a piston and expand it. So you could put all the molecules on one side. You could close the door. You could attach a piston, and you could get some work out. So you could convert the demon's intelligence into his efforts into work. But how do you make a cycle out of it? Well, you need to then erase. This is the punchline. You need to erase the memory of the demon. And so you need to take all the ones and zeros you need to put them all back to 0, let's say. Because you either switch a 0 to a 1 or you don't. You can't start with a random memory. You need to reset it and then do something or not. That takes work, okay? And that work is then heat goes. You generate heat into the surroundings. So if you actually made a cycle out of this thing, it would be you would get nothing out of it, okay? So anyway, that's Maxwell's demon. He's a cool dude. You could get a whole book. I have both the first and second edition. That is a compendium of like probably 50 or more of the most important scientific papers written by people trying to sort this out over, 100 years or so. So get it from the library and read it. Okay, we better get back to work, though. I'm going to move on here. So that stuff is interesting. Maxwell's demon will probably never show up anywhere. But Maxwell's demon has shown up on a PChem final exam, so it's possible. But the other stuff will, but not till the final. Don't worry about it for the midterm. But, we need to move on. And so we're going to move on to what we call Focus 4, or that's what Atkins calls it. And this is what I guess he calls physical transformations. In, rather than chemical transformations. Chemical transformations, definitely we have to get there, right? And the other, we more commonly call these things phase transitions, okay? And we can understand stability, of phases. And what do I need by phases? You'll see. You probably know, in fact, but I'll say it when I get there. So, phase transitions, of course, were well known long before thermodynamics. They happen. It gets cold out. You have to scrape your, not so much here, but if you live in a real place like Nebraska, right? Is this a real place? I don't know. But I like Ithaca, New York. I spent 5 years there in graduate school, and it would rain and then it would freeze. And I remember one time I came outside and I turned on, the windshield was, I could not see through the windshield. So I turned on the windshield wipers. Was this a good idea? No, because the windshield wiper blades stayed where they were, and the rest of it went like this. The windshield wipers were frozen to the windshield, okay, and they broke off. This was probably a 1960 Corvair I was driving at the time. Anyway, phase transitions have been happening, but to understand what's going on, we can use our thermo, right? And this is where I've mentioned it, I think, but we'll mention it again. The chemical potential is really the interesting quantity. And for a one component, and one component means that there's one thing, like water, okay? For a one component system, and the symbol we use is mu, right? Mu is G divided by N. So this is the number of moles. So like if I happen to have G, so if I have a system that's got more than like some arbitrary number of moles in it, it has a Gibbs free energy, an extensive quantity, right? It also has a chemical potential, and it's just I divide the G by N. It's the molar. So it's the molar Gibbs free energy, right? And I'll ask. This will be, well, maybe I shouldn't ask this on the final, but I'll ask you now: is the chemical potential extensive or intensive? It's intensive. Because it's the ratio of two extensive quantities. If I double the system size, the number of moles doubles, the Gibbs free energy doubles. Now in general, and this is defined, I'll have, G will be a function of Tp, and N. This is for the one component system. And G of Tp N is equal to N mu of T and P for one component, O N E. So I just rearrange that equation. But the in general part is down here. If I have R components, like if I'm doing chemistry, so I have H2 plus H2, 2H2 plus O2 gives me 2H2O. There's a reaction, right? I have three things, H2, O2, and H2O. And I have the number of moles of H2, the number of moles of O2, and the number of moles of H2O. And I mix the H2 and the O2. I put them in the balloon. Does the guy with the balloon, does he still have his balloon? No, I guess not. I put them in the balloon, and then I bring the match up. And then the number of moles of H2, O2, and H2O change, right? And, of course, delta G, that's the thing we're going to be paying attention to figure that out. But, so then the G of the system depends on N1, N2, and N3, for the three components. But if I have R components, then that's the G depends on temperature, pressure, and all the different mole numbers, right? And my dG is minus S dt plus V dP plus, and then I've got a sum, J equals 1 to R, mu sub J dN sub J. Because if I change the mole numbers, the Gibbs free energy changes. And so mu sub J is partial G, partial N sub J, and then I have to hold T, P, and then N, K not equal to NJ. Oh, that's actually not mathematically correct. Holding all the NKs constant when K is not equal to J. So I have to hold, like if I want the chemical potential of H2, I take the derivative of G with respect to the mole number of H2, and I hold the other ones constant. Okay, and that's what I mean by chemical potential. And that definition reduces. In that case, if I take the derivative of G with respect to just one thing, then I get mu. So that this equation fits that pattern. But this is the most general thing. And when we decide if a chemical reaction will occur spontaneously or not, guess what we're going to do? We're going to know the chemical potentials of the ingredients, and we're going to figure out, how the ends change to satisfy that. Yes, question. It's more like the way I think about it. Well, okay, so like if I have charged, maybe this is like I think of it as like an electrical potential. So like I have a certain situation and I have charged particles, okay, and if they're over here versus they're over there, they have a different potential, okay, right, and so they might want to move based on that potential. And the chemical potential is like that, but they're moving in a space of chemical identity, right? So it's a bit more abstract. Go to a rave, and then afterwards it'll all be clear how it works. I'm not encouraging that, but you have to expand your mind. Find the caterpillar with the mushrooms and ask for the mushrooms. So you're moving in some sort of other space. But like if I have a high chemical potential, like if the reactants separately have chemical potentials that are higher, and then they can rearrange their identities and make products that have a lower chemical potential, that'll happen spontaneously. So it's in relation to other things. But we'll get to chemistry. But right now we have the same thing that we can talk about for just the for physical changes. So I have mu for a single component. And if I draw, yeah, let me just draw this picture, and then we'll pick up, of course, later. Let's say I have a closed container. Okay, so this is a cork. And I could imagine doing the following. I could put a piece of ice. And you know, this is ice. Let's say isothermal. So I have a temperature T naught, and the beaker lets heat flow. So I take a block of ice and I put it in an evacuated. This thing would break if you tried to. Don't do this, okay? But if I had an evacuated volume and I put ice in there, and heat could get in there, what'll happen? And so there's vacuum with the solid. What happens? Well, some of it's going to melt, right? So I have a total amount in there, and so there's some liquid that forms, right? And there's some vapor. So I have ice, which is solid, water, which is liquid, and I have vapor, gas, and water vapor. And you know, the ice cube would really be floating, but it's not that much water, so it's just sitting on the bottom. That'll happen spontaneously. But then eventually what'll happen? If I wait long enough, I'll have this situation. I'll have some solid, I'll have some liquid, and I'll have some vapor in equilibrium with each other. And when this is at equilibrium, so the stuff isn't still melting. I have the solid, the liquid, and the gas